Question number 1. Give the ground state electron configurations and the bond orders of lithium-2, beryllium-2, carbon-2. Now, for most of the questions involving molecular orbital theory, the first step is choose the correct energy diagram. So, for the molecules made of lighter atoms, we choose the energy diagram that put 2 sigma g above 1 pi u. Okay, and then the next step is to count the valence electrons. So for lithium atom, it's 2s1. Now you have 2 lithium, so the total valence electron is 2, and both goes to 1 sigma g. And so the electronic configuration is 1 sigma g2. The bond order is calculated by half number of electrons in the bonding minus anti-bonding. So in this case, there's no anti-bonding electron, so half times 2 electrons, and that gives you bond order 1. Now, if you are not familiar with this material, please watch the video of lecture notes. Okay, so for beryllium, the atomic electronic configuration is 2s2. So total is 4 electrons, and then the next 2 goes to 1 sigma u. All right, so electronic configuration 1 sigma g2, 1 sigma u2. And the bond order should be 2 minus 2, because this is 2 sigma u is an anti-bonding molecular orbital. So 2 minus 2 is 0. So bond order is 0. For carbon, 2s2, 2p2. So you have 4 electrons times 2, it's 8. So 8, 2 goes to 1 sigma g, 2 goes to 1 sigma u, 4 will goes to 1 pi u. Okay, remember 1 pi u has 2 degenerate orbitals. Okay, so you can hold 4 electrons. Okay, and therefore the electronic configuration is 1 sigma g to 1 sigma u to 1 pi u 4. Okay, we also know this 1 pi u is a bonding molecular orbital, and therefore it's half 4, so it's 2. Okay, so bond order 2. Now you don't need to count this 1 sigma g, 1 sigma u, because both are occupied. They cancel each other. All right, so that's question 1. Now question 2. From the ground state electron configuration of boron to carbon to predict which molecule should have the greater bond dissociation energy. Now, bond dissociation energy is a measure of bond strength, and bond strength is parallel to the bond order. So again, we want to go back to calculation of bond order. So for carbon, we already calculated the bond order is 2. So what about the boron? Now, boron electronic configuration for boron atom is 1s2, 2s2, the valence electron, 2s2, 2p1. Okay, so the total electron is 3 valence electron times 2, that's 6. So 2 goes to 2 sigma g, 2 goes to 2 sigma u, and 2 goes to pi. So that goes to pi. Okay, so electronic configuration for boron is 1 sigma g to 1 sigma u to 1 pi u2. That's 6 electrons. And the bond order, now again, these two cancel each other, so you only have 2 electrons in the bonding molecular orbital. So 2 divided by 2 is 1. So bond order is 1. For carbon, we already calculate it's 2. Now because carbon 2 has a larger bond order, and therefore it's stronger bonds. All right, so the answer is carbon 2 should have greater bond dissociation energy. Experimental show boron 2 is 4 electron volts, and carbon 2 is 6 electron volts. Question number 3. Arrange the species O2 plus, O2, O2 minus, O2 2 minus in order of increasing bond length. Now bond length is related to bond order. So again, we need to calculate the bond order. And to calculate bond order, we choose the right energy diagram for oxygen, and this is the energy diagram. And note that 2 sigma G is below 1 pi U. And next step, calculate the number of valence electrons. For oxygen atom electronic configuration, valence electron is 2s2 2p4. Okay, so you have 4 or 6 valence electrons times 2 because it's O2, and therefore it's 12 electrons. Okay, that's the electronic configuration. So 2 2 2 4 2. Okay, that the total is 12. Now to calculate bond order, all right, these two, because they already both occupy, so they cancel each other, and these 6 are bonding molecular orbital, and these are anti-bonding molecular orbital. So now you have 6 bonding, 2 anti-bonding. So 6 minus 2 is 4. 4 divided by 2 is 2. So for oxygen molecule, the bond order is 2. So now let's look at the first one, O2 plus. Means you lose the electron. So the highest energy molecular orbital lose 1 electron. So the electronic configuration is 1 pi G1. And since you lose the electron from this anti-bonding molecular orbital, the molecule should become stronger. The bond order should become larger. So let's calculate. 6, now this becomes 1. So 6 minus 1, because you remove 1 from anti-bonding, and so you have more electrons in the bonding compared to anti-bonding. 6 minus 1 is 5. 5 divided by 2 is 2.5. So bond order becomes larger. The bonds become stronger. Now for the O2 minus, it means it gains electron. The electron goes to the 1 pi G. So the 1 pi G has 3 electrons in the anti-bonding molecular orbital. You put more electron in the anti-bonding, the bond order should decrease. 6 minus 3, and that gives you 3 divided by 2 is 1.5. Okay, so O2 you get actual more electron, so that's 1 pi G4. 4 electron in the anti-bonding, 6 electron in the bonding. 6 minus 4 is 2. 2 divided by 2 is 1. So bond order is 1. So next, what about the bond length? Remember, stronger bonds, shorter bond length. Longer bonds, weaker. Okay, longer is weaker bond. So here the strongest bonds, the bond order 2.5. So O2 plus, that's the strongest bonds. Stronger bonds, shortest bond length. So we start with O2 plus, and then O2, and then O2 minus, and then O2 2 minus, which is the weakest bonds. That is longest bond length. Question number 4. Predict which one has the higher vibrational frequency, fluorine molecule or fluorine cation. Now, fluorine vibrational frequency is related to the force constant. And force constant is a measure of bond strength. And so, again, we need to look at the bond order. To calculate the bond order, we need to look at the energy diagram. And here is the correct energy diagram for fluorine. And the valence electron for fluorine is 7. It's group 7. So times 2, that gives you 14 electrons. Okay, so now we fill the molecular orbitals. 2, 2, 2, 4, 4. That's total is 14. Okay, so to calculate the bond order, we notice these two cancel each other, and these are all in the bonding molecular orbital, and these are the anti-bonding molecular orbitals. So you have 6 in the bonding, 4 in the anti-bonding. So 6 minus 4 is 2. 2 divided by 2 is 1. So for fluorine molecule, bond order is 1. For fluorine cation, the molecule lose an electron from the highest energy molecular orbital, and so that give you 1 pi g3. So now the anti-bonding molecular orbital, we have 3 electrons, and therefore 6 minus 3 is 3. 3 divided by 2 is 1.5, and therefore when fluorine loses an electron, it is from the anti-bonding molecular orbital, so the bond becomes stronger. Okay, and because bond becomes stronger, it has a higher vibrational frequency. Question number 5. What is the speed of a photoelectron ejected from an orbital of ionization energy 12 electron volts by a photon of radiation of wavelength 100 nanometer? So in photoelectron spectroscopy, the incoming lights, so here is the energy of incoming photon, which is absorbed by an electron in a molecular orbital, which can be ionized. That's the ionization energy, and the extra energy becomes the kinetic energy of that electron. So the energy coming in becomes kinetic energy, and also ionization energy. So in this question, the ionization energy is given, the wavelength of incoming light is given to calculate the energy of the photon, and therefore we can calculate the speed of the electron. Okay, so just modify this equation, so the speed can be calculated by 2 times hv. V is the frequency of light, and ionization energy. Now we in this case we know the wavelength, not the frequency, so you need to use the speed of light divided by wavelength. That give you the frequency. So here Planck constant, speed of light, wavelength, note that it's nanometer, so you times 10 to the minus 9, and ionization energy 12 eV need to change to joule, and this is conversion factor to change eV to joule. All right, and the mass of the electron. So the answer is 3.86 times 10 to the 5th power meter per second. Question number 6. Give the ground state electron configuration of CO, NO, Cn-. So note that these are about heteronuclear diatomic molecules, and the energy diagram is similar to that of homonuclear diatomic molecules. For example, 2s orbital forms 2 molecular orbitals. One is bonding, one is anti-bonding, and both are sigma bonds. And the p orbitals forms 6 molecular orbitals, 3 bonding, 3 anti-bonding, and the pz atomic orbital forms a sigma bond, and px py forms 2 pi bonds. So these all look similar. The only difference is that because carbon monoxide, carbon, oxygen have different electronegativity, so the energy of the 2 atoms are not at the same level, and the more electron negative one, for in this case is oxygen, should have a lower energy level than carbon. So similarly, the 2s orbital are not at the same level. Oxygen 2s orbital is lower than carbon 2s atomic orbital. All right, so that's the only difference. So now we count the valence electrons. For CO, the valence electron is 2, because carbon has 4, oxygen has 6. So that's total of 10 electrons. 2 goes to 1 sigma orbital, 2 goes 2 sigma, 2 goes 3 sigma, and then so that's 6, 1, 2, 3, 4, 5, 6, so 7, 8, 9, 10. All right, so that's 10, and therefore electronic configuration should be 1 sigma 2, 2 sigma 2, 3 sigma 2, 1 pi 4. Okay, for NO, the valence electron is 11, so you add one more electron, so that electron should go to 1 pi or 2 pi anti-bonding molecular orbital. All right. And then for CN minus, the valence electron is also 10 electrons, same as CO. So electronic configuration is also same as the carbon monoxide electronic configuration. Question number 7. Sketch the molecular orbital energy level diagram of xenon fluoride and deduce its ground state electronic configuration. Is xenon fluoride likely to have a shorter bond length than xenon fluoride cation? So this is a heteronuclear diatomic molecule, and the energy diagram is similar to question 6. And we place the two atoms at different energy levels. So fluorine has a lower energy than xenon. Okay. Also note that xenon use 5s, fluorine use 2s as their valence shell orbitals, and the molecular orbital formed are very similar. So 1 sigma, 2 sigma, that's an anti-bonding, and then sigma bond, and then pi bond, and the anti-bonding 2 pi bond, and the 4th sigma bond. Okay, very similar. So calculate the electrons, valence electron. Xenon has 8, fluorine has 7, so total 15. All right, so 15 electrons. So 2 here, 2, 4, so 2 more or 1 more. Okay, that gives you 15 electrons. All right, so electronic configuration is 1 sigma 2, 2 sigma 2, 3 sigma 2, 1 pi 4, 2 pi 4, 4 sigma 1. All right, now notice that these are the bonding, these are the anti-bonding. Okay, and if we remove an electron from this sigma 4 sigma molecular orbital, that will be xenon fluoride cation. And because we remove electron from anti-bonding, you expect the molecule bonds become stronger. Okay, in fact, we can calculate the bond order for the xenon fluoride neutral molecule. The bond order is 6 in the bonding and 5 anti-bonding. 6 minus 5 is 1, divided by 2, so it's 0.5. So for this one, the bond order 0.5. After you remove electron from anti-bonding, so here you have 4. 6 minus 4 is 2. 2 divided by 2 is 1. So the cation bond order is 1, and therefore it becomes stronger. Okay, so when the bond is stronger, the length becomes shorter. All right, so therefore the xenon fluoride cation, its bond order increase, and therefore its bond length is shorter.